Okay, now we're taking a look at 3.7 topics in the theory of polynomial functions, part 2. We begin this section by first observing a theorem called the conjugate zeros theorem, which tells us that if p of x is some function with only real coefficients, then given a zero such as a plus bi, where notice guys there's an imaginary part on this conjugate number, then we are required to also have basically the conjugate of this also present as a zero, a subtract bi. So the idea is that these, because we know conjugates when they multiply they cancel out the imaginary, so both zeros must be present in order to give us those real coefficients that we're looking for. So the main idea of this section is to start building polynomials from scratch given their roots. We're going to do that with real roots, and we're also going to start incorporating imaginary roots also. So that's when this theorem is going to start becoming useful to us. If you look in your PowerPoint now, on slide 3, we have an example. And this example asks us to please find a polynomial having zeros 3 and 2 plus I. It also gives us a requirement to satisfy, saying p of negative 2 is equal to 4. So here we know that we have zeros 3 and 2 plus I. That's the first piece of information we should use. As we build this polynomial, remember guys that when we know a zero such as x equals 3, as we translate this, the idea is that we need to write this in opposite form as a factor. So in other words, this will translate into x subtract 3. So that's going to be the first piece that we're going to multiply into our polynomial. The next piece here, this 2 plus I, we can write this number, this x equals 2 plus I would be the literal way we could write 2 plus I as a 0. When we translate this into factored form, we can write x subtracting this piece, 2 plus I. And then of course, like we just now observed through the theorem that we just learned, x subtracting the conjugate of x plus 2i would be x subtracting 2 minus I. So now we have all three roots that the problem is telling us about. And the main idea here is that we're going to start foiling to solve for this polynomial. I'm also going to add an a factor on the front of this polynomial so that at the very end we can solve and see if there's any kind of adjustment factor that has been multiplied into this polynomial. To solve for a in just a few minutes, what we'll use at the end to solve for our a factor is we're going to use the piece of information that told us when x is negative 2 that y would be equal to 4. Okay, so let's go ahead now. First we'll start by distributing the negatives on both of those roots. So we have x subtracting 2, negative I. We also have x subtracting 2 plus I. And then we still have x subtract 3. Now we can just fully multiply through both of these roots. I'm going to say x times x is x squared. Then I'll take the negative 2 and hit that with the x, so that's negative 2x. The negative I with the x is negative ix. And now let's start sharing this negative 2 through the next piece. So we have negative 2x. We have positive 4. And we have negative 2i. Let's see, so we've now shared the x, we've now shared negative 2. Now let's go ahead and go through sharing the negative I. So we have negative I times x, which is negative ix. We have negative I times negative 2, which is positive 2i. We have negative I times positive I. Positive times a negative would be a negative, and then of course we're getting an I times I, which is I squared. So let's see, we know that's equal to negative 1. I'll go ahead and make a note of that. And let's go ahead and clean this up a little so that we can then take a look at multiplying x minus 3 through this new piece of the polynomial that we've discovered. Let's see, we have, for both of those actually, negative ix's. Negative ix. let's see, I see the I squared, the negative 2x, the negative ix. I'm just proofing this for a second because I did expect we have okay, so actually this one right here should have been a positive ix. So I am glad that I stopped to proof that because I noticed that when we multiply, let's see, we had the x times x, the x times negative 2x, and then the x times positive I right there would have given us that positive ix. And again, the reason I knew to look back to the work for that, and the reason you would have known if you had been doing this yourself, is because we do expect all of our imaginaries to fully cancel off of this. This is part of the reason that I have chosen to multiply these roots of complex numbers first, because we know the imaginaries should cancel off and the problem should clean itself up pretty well. So let's see, here we're going to go ahead now and cancel the ix, the negative ix, the negative 2I, the positive 2I, and we already saw that the I squared turned into a negative 1, which is the same thing as a positive 1. So now we're left with just real number coefficients. As we combine these things, we have x squared. We have negative 2x minus 2x, which gives us negative 4x. And we have 4 plus 1, which is 5. So we have x squared minus 4x plus 5, now being multiplied by x minus 3. So we'll fully share this binomial of x minus 3 through the x squared piece of this. First we'll say x times x squared gives us x cubed. Then we'll say x times negative 4x is negative 4x squared. And x times 5 is positive 5x. Next we'll share this negative 3, giving us negative 3x squared. Negative 3 times negative 4, positive 12x. And negative 3 times 5, which is negative 15. Let me rewrite this. And let's see, do we have any pieces that we can combine as far as like terms go? It looks like certainly we do. We don't have any x cubed terms, so I'll write the one that we do have. We don't have any that we can put together. We have negative 4 minus 3 is negative 7x squared. We have 5x plus 12x, so that's going to be plus 17x. And we still have our negative 15 on here with our a in front. Okay, so we have this beginner piece to our polynomial. So the next idea, again, is at the very end we said that we would go back and then solve for that factor a, just to make sure that our main polynomial had not been adjusted by some multiple. So to do that, what we'll do now is we'll say, okay, well, I know that p of negative 2, meaning when x is equal to negative 2 is equal to 4. So I'm going to change p of x into a y value of 4 because that's the output that is going to go with an x of negative 2. So everywhere I have x, I'm now going to write negative 2. So we are literally substituting in the given x and the given y so that we can solve for our final variable of a to see what that might be. Okay, so after substituting in that negative 2 and simplifying, we find that everything comes out to equal negative 85, where that negative 2 was put in. So now we have 4 equals a times negative 85. To get a alone, let's now divide by negative 85 on both sides. So our a factor is negative 4 over 85. And that fraction cannot be reduced easily into anything cleaner. And the decimal form of this fraction, it looks like that is not a terminating fraction. It appears to be irrational. So we'll just, or not irrational, excuse me, it just appears to be a messy decimal. So we'll leave this in fraction form so that it's a little bit cleaner. What this means to us now is that we now have a polynomial, p of x, equal to negative 485 in front of everything that we just solved for, which was x cubed minus 7x squared plus 17x minus 15. This right here is actually sufficient for our purposes. However, if we wanted to see a fully simplified version, what we could choose to do is we could go ahead and take this coefficient And we could choose to simplify this polynomial by multiplying negative 4/85 through the entire thing. So let me go ahead and write what that would be also, just in case you are ever trying to look and compare your answer with perhaps an answer key or with a friend that you're studying with. Let's see. So here we have this fraction being multiplied by negative 7. That will give us positive 28 over 85x squared. We have 17 times negative 4 over 85, which will give us, I'm going to keep everything in fractions to be consistent, that will give us a negative 4/5 x. And then lastly we have negative 4/85 times negative 15. Let's see, if I math fraction that one, I'm getting positive 12/17. So again, both of these are the exact same as far as being equivalent. It is preferable to go ahead and distribute, but I will not be requiring you all to do that. Just make sure that you understand the concept of how to multiply that negative 48/5 through, or negative 4/85 through, if you need to. Okay, so this is the end answer of our first slide, slide 3. Please try on your own slide 4, then now you try to see if you can do something very similarly. The next thing that we're going to explore is called the fundamental theorem of algebra. Basically, every function defined by a polynomial of degree 1 or more has at least one complex. Remember, guys, that complex means real or imaginary 0. This is followed by the number of zeros theorem. So I'm going to actually write the number of zeros theorem out here for you. Hopefully you are referring to this PowerPoint during this lesson to help you as you're visually learning this. But as far as this theorem goes, the idea is that a function defined by a polynomial of degree n has at most n distinct, unique, complex zeros. So here are some of the basics. Degree n, at most n unique, complex zeros. This is actually something that we all observed as a class in section 3.5 recently when we were looking at basic characteristics of polynomials. So this is just kind of reiterating that if you know the degree of your polynomial, you know how many different zeros it could have. As we go through this section and we're observing the zeros, you are going to notice that you can count zeros that are repeating and add up to the degree. So that's the reason it says at most n unique, because it is possible to have repeating roots on these polynomials. Okay, so on this example here, we're going to kind of explore this idea of different zeros. On slide 6 of our PowerPoint, the example says find all complex zeros such that p of x is equal to x to the 4th, subtract 7x cubed, adding 18x squared, subtract 22x plus 12. Given that 1 subtract x is a 0. So we're being given one 0 that we are being asked to solve for every other 0 that's present. So the idea is first we have 1 minus I, 0. We know that based on the theory we learned at the start of this PowerPoint, we also have another 0 guaranteed. 1 plus I would also be a 0. So we can go ahead and make a note here that we know, just based on the rules, that we definitely have to have both of these zeros. So now let's go ahead and start using some division to divide these things out. We can actually use synthetic division here, because if I were writing this 0 in factored form, I'm just going to say recall here so you can visually see what I'm talking about. If I were writing this 0 of 1 minus I in factored form, it would look something like x subtracting 1 minus I. So notice here that it does qualify for synthetic because the x has no coefficient and the degree on this x is just a 1. The same thing would apply to the 1 plus I. So for synthetic here, we will use the actual root, 1 subtract I. And let's see, on our polynomial it appears to be adjusted. We have 4, 3, 2, 1, none. For the powers on those x's. So writing the coefficients, we have 1, -7, 18, -22, and 12. Okay, we'll drop the 1 here. And we're going to follow the same exact pattern that we followed using synthetic division with just real numbers. So we're going to say 1 times 1 minus I is going to be 1 minus I. And as we put these together, we'll say, okay, -7, I'm going to put that with its like term, which is a positive 1, giving me a -6, and I still have negative I. The next step takes that -6 minus I and multiplies it by 1 minus I. I'm going to go over here on the right-hand side of the paper and do that by hand. Remember, if you have your calculator in complex mode, you can also use technology here to help speed you up with this multiplication process. So here I'm going to write on the side for side work. 1 minus I being multiplied by -6 minus I. Foiling this out, let's see, we get -6, negative I, positive 6I, and we get positive I squared, which is a -1. So it looks like we actually have -6 minus 1, that's a -7, and we have plus 5I. So here we have -7 plus 5I. Whenever we combine these now by addition, we have 18 minus 7 giving me 11 plus 5I. And now we need to multiply once again. So we have 1 minus I being multiplied by 11 plus 5I. So now when we FOIL this, we have 11 times 1 is 11. The outer is going to be 5I. The inner is going to be -11I. And the last is going to be -5I squared, which is -5 times -1. That's the same thing as a positive 5. So here I'm seeing a 16 minus 6I. Now we have -22 being added to 16 minus 6I. So let's see, 16, 17, 18, 19, 20. That's going to be a -6 that we have here, minus 6I. Now to multiply this piece, we will have, again keeping the scrap work on the right, 1 minus I being multiplied to -6 minus 6I. So the first two pieces gives me a -6. Outer, we're getting -6I. Inner, we are getting positive 6. And with the last, we are getting a positive 6I. So here it looks like we have our 6I's canceling and our 6's canceling, so that we are getting a 0. Okay, so on this very last FOIL right here, squared on that 6I squared, whenever we multiplied our -I times -6I, just please make a note here that you're actually getting a positive number, but you are getting I squared, which is a -1. The reason this makes a difference is because our -6I and our positive 6I still cancel, but that leaves us with -6 minus 6, which is actually -12. This is more of what we were expecting, because it will give us a remainder of 0, meaning that this actually is a perfect 0 in our polynomial. Okay, so here we've successfully divided out the first 0. And we have this polynomial here with these coefficients left over. We could go back in and write things like, let's see, that would be 1x cubed, and then counting down x squared on the next piece, x to the first, then no x, if we wanted to. But really, guys, you don't need to start translating this yet. Let's just continue dividing. So now for the next 0 that we have 1 plus I coming out of this piece. And I'm going to use all of those coefficients that I was just now talking about that we found. We're going to continue dividing by using stuff that we've just found. So we're going to extract out one more 0 to get the rest of these. Okay. So here we drop down our 1. And we have that 1 times 1 plus I is 1 plus I. This gives us a -5, and our i's will cancel. Now we will multiply -5 times 1 plus I. That gives me -5 minus 5I. Look how nice this is, guys. The i's are canceling on our complex numbers. Now we have 11 minus 5, which is a positive 6. Here we will be getting a 6 plus 6i. Also very nice because we are getting a remainder of 0. Now it's definitely time to go back and start translating what we have. Remember, looking back at the top now at this polynomial, that the degree of our original polynomial was degree 4. So again, like I said a second ago, if we'd wanted to go in there and write the next level down, we would have had degree 3. And then here we would have x to the second, which is degree 2 on this polynomial here. Meaning this next piece, negative 5, has an x on it, and then 6 will have nothing. So basically what we've found so far, at least conceptually speaking, conceptually, we have now extracted x subtract 1 minus I. That's one of the roots we pulled out. We have also extracted this other one, which was 1 plus I, and we have found that those two roots being multiplied by x squared minus 5x plus 6 give us our original polynomial back. So the idea now is to try to simplify by either factoring or using our quadratic equation this x squared minus 5x plus 6. So the first thing that you would actually want to do here, it would be to try to factor this. So let's see. Using the grouping method that we have used in class, let's find multiply add, two numbers that multiply to be 6 and that add to be 5. Actually have to add to be negative 5. Let's be careful there because that could make a big difference. So multiply to be 6, add to be negative 5. We can test out some things like perhaps 2 and 3. Let's see. If both of those are negative, those would both add to be negative 5 and they would multiply to be a positive 6. Also remember that when you have coefficient of 1 in front of your x squared term, you are allowed to factor immediately with those two numbers you've just found. So we will have x minus 2 and x minus 3. So the directions of this problem, remember, the directions will be what are really tricky when you get to this test, so make sure you do pay attention to what you're supposed to do. The directions of this problem said to please find all complex zeros. So far what you are looking at would be a fully factored form of p of x. So we've successfully factored this polynomial, but the question has actually asked us what all the complex zeros are. We knew initially that we had complex 0 x equals 1 minus I. We also knew that we had 1 plus I based on the theorem we had learned, so that's one of the ones we actually kind of found. And now we have found two other zeros. Let's see, when x minus 2 is equal to 0, if I were solving this to become a 0, we'd get x equals positive 2. So I'll say 2 is one of our zeros. And the same thing holds for x minus 3, remembering that it becomes the opposite. When x minus 3 is equal to 0, that actually solves out to be x equals positive 3. So all of the complex zeros here, we have 4 of those, are right here. And remember, we did expect to have, up to 4 distinct roots here. Distinct or unique roots. Because our degree on that original polynomial again was a 4. Now in your notes, please try slide 7 and see if you can also divide out all of the complex zeros. You will notice that on slide 7, you're not even given an imaginary. So this should be a pretty fun little exercise for you that's not quite as in-depth as the one we just now did. Okay, so for the final portion of this PowerPoint that we're going to look at ahead of time together, we are on slide 8, multiplicity of a zero. The idea is that multiplicity of a zero refers to the number of times a zero appears when you factor a polynomial. So notice here I have an example for you. P of x is equal to x to the 6th power plus x to the 5th minus 5x to the 4th minus x cubed plus 8x squared minus 4x. So notice that is equal to the factored form that I have written right below it. Notice here, for example, that we have here on this first x, an x to the power of 1 that corresponds to a root or a zero that is 0. So right here we see that x equals 0 is a single multiplicity 0. Single meaning the power on that root in factored form was simply a 1. Now on the next one, however, this x plus 2 squared please notice that this one has multiplicity 2. And notice that it corresponds to an x of negative 2 if you had solved this x plus 2 equal to 0. So down here below I'm going to make the note that x plus 2 squared corresponds with x equals negative 2, which is a 0 of multiplicity. Two. The last one that we have in this example is x subtract 1 cubed. If we set that equal to 0, that would correspond to a 0 that is x equals 1. So here, down on our notes, I'm going to write x equals 1, a positive 1, x equals positive 1, would be the 0 that this piece corresponds with, and this piece has multiplicity 3. So let's see. Please make an observation with me that the degree of your original polynomial, degree, was equal to, or is equal to, 6. Now, even though we only have 3 distinct roots, notice something about the powers of these roots. The first root has power 1. The next root has power 2, or degree, multiplicity 2. And the third one has multiplicity 3. So if we add those up, 1 plus 2 plus 3, notice that these still will add up to equal a 6. So while we didn't get the full 6 as far as unique or different zeros, after we factored this polynomial, we were able to see that we had some multiplicities on those zeros that would still make them add up to be 6, which is pretty cool, because if you add up the powers like that on your factored form, you will know when you have solved for all of your zeros. Now, the multiplicity goes beyond just knowing that you have all of your zeros when you've solved. It's actually also special because multiplicity will tell you how your function, here we'll say p of x, touches the x-axis. So the idea is that whenever I have an odd multiplicity, such as this x to the first, my polynomial will cross like an x to the first function. It will actually almost cross just like y to the x would cross, like a line. So it crosses the x-axis in a linear fashion. For an example of an even power, here we had a multiplicity of 2. Please note that that means the polynomial p of x would either bounce on perhaps the positive side of the x-axis, or perhaps it would bounce on the negative side. But the idea is that the way that the polynomial would hit the axis is it would not actually cross through. It would instead bounce on the x-axis in the form similar to that of an x squared function. It's a very cool thing to notice here, that the behavior of the polynomial very close to its 0 is going to actually look almost like the parent function concerning the power of that root. So whenever we have a root to the power of 2, it's going to behave almost like a quadratic, real close to the point where it's hitting the x-axis. And the same thing would go for that power of 3. If we were looking at our, let's see, it was our x minus 1 factor that was multiplicity 3, we would notice that it's crossing almost like a cubic function. So if we got very close to the x-axis, we would either see something of this nature or something of this nature. And this can be very small. The idea, though, is that it would cross in a fashion similar to a cubic function. Very close, and I'm not a very good artist, just imagine that it's doing its curvature shape, that little cubic stuff, very close to that point. That's what I'm trying to illustrate here on the picture. But the idea is that it's going to cross the axis in the same general shape that a cubic function would cross. Some other general patterns besides just the shape would be that when you have an odd multiplicity, notice that it passes or crosses completely through the x-axis. So if you recall from section 3.6 when we talked about the intermediate value theorem, this is the type of x-intercept that we were talking about when we were testing our polynomials for a sign change as they cross through the x-axis. This other type of x-intercept or root, where we have an even multiplicity, these tend to bounce, and this would actually be extendable to even x to the power of 4, or a root to the power of 4, that kind of thing. But the idea is we are not seeing a sign change, even though we do technically have an x-intercept. What I'd like for you to do now, please, is observe slide 9 and just look at those general shapes. In fact, you may want to graph those functions that we have on slide 9 and just notice the different kinds of shapes that you are getting at your roots. So the last thing that we are going to do to kind of bring this full circle today in this discussion is we're going to construct a polynomial, since that was one of our number one goals in this section. We're going to construct a polynomial, given some information, not only what the zeros are, but actually what the multiplicities are that go with those zeros. So on slide 10 of your PowerPoint, the directions say, please find a polynomial function with real coefficients of the lowest possible degree, having a 0, 2 of multiplicity 3, a 0, 0 of multiplicity 2, and a 0i of single multiplicity. So let's see, we're supposed to find p of x to the lowest degree possible. And the direction said, given a 0 of 2, multiplicity 3, a 0, 0 of multiplicity 2, and a 0 I of single multiplicity. Before we write this, please remember the theorem that we've discussed just a few minutes ago. If I have I as a 0, that means I must also have its conjugate as a 0 as well. So here I'm going to remind you that we have negative I also. So as we start to construct our p of x is equal to, we're going to take the opposite of every 0 as we put this polynomial in factored form. So here we have, corresponding with the 2, we will have x subtract 2. Multiplicity 3 means put a power of 3 on that. Then we have 0, 0, which means basically just a plain x. Multiplicity 2, so we'll say x squared. And then we have 0i to the single multiplicity, which would mean x minus I, because it's always the opposite in parentheses. Single multiplicity power of 1, and then we have to put its match, which is x. This would actually be subtract negative I, which you guys know is the same thing as adding an I, since we're changing the negative to a positive here in parentheses. So this is the original polynomial. And then, of course, technically what we would like to do here is we'd like to go ahead and multiply this thing down to see what it looks like after we've FOILed all this out. That's something that I encourage you to do so that we can pick up in class and discuss what this polynomial looks like. I will make some further comments for you, though. Please notice, even before you start multiplying, that we have, let's see, we have 3, 1, 2. Right here we have a single degree, so that would count as 1 and 1. We are expecting to get a polynomial of 3, 4, 5, 6, 7. So we will have x to the 7th power after you multiply this out, with some coefficient, of course, and all those terms in between. So that's something for you to try on your own. I'm going to say, please try foiling this polynomial that I've set up for you on your own so that we can discuss your results later. Okay, that's it for now for section 3.7.